at least, is that, well, they're very dense. Therefore, the matter inside neutron stars is very compact, and it doesn't move around. So that means that the moment of inertia of the star is very constant. And also, there's a superfluid, which moves, but not to change the moment of inertia, but it moves in the sense that it might move in its own, and it might not be totally coupled to the rotation of the rest of the star. And we will see what the effects of this can be. We study the rotation pulsar timing, in which we essentially measure precisely the arrival times of pulsars on Earth and analyze them to account for the rotation of the pulsars over long periods of time with very high precision. So we can actually apply over this data a very ideal rotation scheme in which we use the equation on the bottom, which is the phase of the rotation, and it's a truncated Taylor series. But in many cases, we only need the first two terms, or well, the first three terms, the frequency of the pulsar and its derivative. And so this frequency derivative comes essentially from the secular spin down of the object, which is we believe a magnetic braking. So because there is a magnetic field, the pulsar has to slow down because the dipole. And given that we have a very steady moment of inertia, because most of pulsars are isolated and not accreting, we can have a very remarkable long-term stability, and we can use this equation to describe the evolution of pulsars over long periods of time. So I've selected a couple of examples here. These are millisecond pulsars that are used in the pulsar timing arrays. The pulsar timing arrays are collections of pulsars that have been studied with the purpose of detecting gravitational waves that are passing through Earth. So for those purposes, they need a very stable pulsars. So if you look at this, these are two pulsars here from this paper. There's some data released in 2018 from the Nanograph collaboration, which is the North American collaboration for pulsar timing arrays. So just look at the top panels of these plots. These are the timing residuals. So these are the residuals of the data after applying a simple model like the one on top. So you can see that they're very flat, there's no structure, and that the RMS of the dispersion of these residuals around zero is very small. In fact, in these cases, is of the order of 1 microsecond. So that means that we can predict the arrival of a pulse with a precision of 1 microsecond or so. In these cases, this on top, there's another case. This is another millisecond pulsar for which over 11 years, only a simple model can describe the rotation. However, have a look at the second plot on the bottom, the top panel only. The others are just other analysis that they did in this paper. But you can see that in this other pulsar, 1937 plus 21, this is another millisecond pulsar, but we can observe this pulsar with very high precision. That means that each measurement of time of arrival is very precise. So you can see that the scale of the variations here is very small. Of the order of 3 microseconds, sorry, around the zero. And you can see that there is variations in some sort of like a wavy style, but it's not exactly periodic. It seems a bit stochastic. And this is what we call timing noise, right? So timing noise is some sort of continuous wandering of the rotational phase around the prediction of a model like the one I showed you before. These are other examples. So on the top, these are 5-year spans or so, a bit less sometimes, of 6 other pulsars. These are not millisecond pulsars. These are normal pulsars. This is the data of a telescope located in Australia, I think. And you can see that also these residuals are not flat. Also, these are residuals for a model with 1 frequency derivative. These are not flat, so you can see structure. The structure is wavy in the sense that it doesn't have sharp feature, and it's something that seems to be continuously happening. In the bottom, there are other examples from a very extended investigation that Hobbs and collaborators did in 2010 with Jodrell Bank observations. And you can see these are other cases in which you can see timing noise in many pulsars. And in others, maybe not, but maybe it's because the error bars are large. And that's indeed something that they conclude in this work in Hobbs, Line, and Kramer in 2010. They studied about 300 or more pulsars. They concluded that the timing noise is intrinsic to pulsar rotation. It's not an artifact of the observation. It's not an instrumental effect. This is how pulsars are rotating. It's common to all pulsars. That means that in these cases that we see in the plots, that we don't see timing noise. We don't see a wavy behavior. It might be just because error bars are too large. But if we increase those error bars, we would see it. Has some sort of a quasi-periodic nature, but it's not exactly periodic. And something that they found also in another paper is that the timing noise perhaps is due to switches between two or more spin down rates. So the spin down rate is the first derivative of the frequency. So what they found is that maybe if you change the spin down rate between two or more states, you generate residuals, phase residuals that actually look like those, like timing noise. So in this work by Line et al. In 2010, in the plot on the left, there is the spin down rate for many pulsars that have the largest amount of timing noise, and in the right-hand side in that plot, it is the timing noise. I mean, the timing residuals of those pulsars, and you can see that many of the pulsars on where you can look at the spin down rate, actually the spin down rate is moving between between two different states, sometimes three different values. This is further proven if you do simulations. So this data in this plot are all simulated data. So we're going to look just at the top ones. So the very top two curves is data simulated for a pulsar that has two different spin down rates that switch between one another periodically. So if you have that, you get a very periodic timing residuals, which is expected. But if you don't do it periodically and do it quasi-periodically, you get some sort of like wavy timing residuals, which is exactly what we see in timing noise. So their conclusion to this point is that it might be possible that all timing noise is caused by two or more different spin down states. There's even more that sort of that adds to this story, and it has to do with the pulse shape of the pulsars of these pulsars. So the pulse profile or the pulse shape in pulsars is generally very stable, and in fact is due to this stability that we can actually do this pulsar timing so precisely. However, some pulsars present variations in the pulse profiles. So let's take, for example, the last one on the bottom of each of these two plots. I will explain what these plots are. So in the left, we have the pulse shape of, let's look at pulse, the pulsar 1822-09, which is on the bottom. So this pulsar has two different pulses so it alternates between one or two pulse profiles. So one of them is one single pulse, and the other one has two pulses. So it has a precursor that you can see in the gray color line. So that pulsar is also plotted on the bottom plot on the right-hand side plot, in which we can see on the top the amplitude ratio between this precursor and the second pulse. So when the precursor is there, we get a larger value, and when the precursor is not there, we get a number close to zero. So we can see that the presence or not of the precursor varies in some sort of quasi-periodic way, and that correlates very well with the spin down rate of the pulsar, which is plotted on the bottom curve on this plot. So, and the same can be observed for the other pulsar. There is some sort of good correlation between the change in the pulse profile and the spin down rate states. So the conclusion is that the spin down rate states correspond to magnetospheric switches. Something happens in the magnetosphere, which is able to change the pulse profile, which has to do perhaps with the amount of plasma that is generating the emission, or perhaps the geometry of the magnetic fields, I don't know. And that is also able to change the spin down rate that affects the rotation of the pulsar. So there's been more studies about this. This is just an example. This is Brook et al. In 2016. They used sparks observations to also study changes in the pulse profiles and their correlation with the spin down rate. So in these plots, I don't know whether you can see them very well, but on, let's say on the top we have the pulse profiles, and these are also pulsars that show two different pulse profiles every some time. So there's the blue and the red one, let's say. And in the bottom, let's just look at the top panel, the presence of one or the other pulse profiles it's on time. So this is time over something like 1,000 days, a bit more. And you can see that the pulse profile alternates between blue and red, blue and red, blue and red. And in the very bottom, the bottom plot, it's the spin down rate. So the first derivative of the frequency. And then you can see that also the first derivative of the frequency oscillates between two values. So they conclude that this effect is also, they confirm that this effect exists. However, they also conclude that this spin down variability is not sufficient to explain the noise observed in the data. So it might be that there's something else. So just to conclude with this fancy photo, this part about timing noise, might be the reflection of magnetospheric variability on the rotation. And this is something that, if we think about it, is expected. If the magnetosphere is not stable over long times, or if it has, if there are processes happening in the magnetosphere, which could be, for example, changes in the density of the plasmas that generate the radiation, we might have different states. And given that the torque that affects the pulsar is actually magnetospheric, it has to do with the magnetic field, and also that the acceleration of particles in the magnetosphere can indeed alter the rotation of the pulsar. It is expected that if there are changes there, we should be able to see that in our timing, especially considering that the timing of pulsars is very precise. However, given the studies that I just described and other studies, this might not be all. So it could also be that the timing noise is in part magnetospheric, but in part it could still be related to the insides of the star. For example, something that reflects the depth of the neutron superfluid that is inside. So I'm going to go back now to this plot in which we have a lot of cases of, these are timing residuals for many pulsars. And so I use this to show you timing noise, because in many of them you can see this wavy behavior. However, I marked here 3 of them that have a different sort of signature, which is a very pointy or cuspy signal in the timing residuals, which means there is a very rapid discontinuous actually change in the slope of the phase, which means that there is a very it's a step in the frequency, and that's a glitch. So this type of signatures is the ones that we call glitches, and in general they're easy to recognize in the timing residuals, in the examples I just showed. But you can already see that for small glitches this is not very easy, which is something I'm going to mention later. So these are examples of glitches in the timing residuals. The plot on orange this is the crab pulsar. So you can see how there are 2 glitches here that I marked with the circles in red, and there's also timing noise. There's this here other examples of glitches. In the case of the glitches on the right hand side plot, these glitches totally dominate the timing residuals. You cannot see the timing noise too much. So what do we understand by glitches nowadays is it's actually a very specific definition. These are occasional spin-up events. It's always a spin-up. In most of the cases, these are spin-ups, they're not spin-downs. And at the same time that we see a spin-up as a negative spin-down rate step. So in this plot, I like this plot because it shows how rare the glitches are. So these are almost 20 years of data in the before the glitch. So this pulsar was slowing down steadily until the glitch happened, and then it just continued doing something like what it was doing before. But it's not exactly what it was doing before, because when you look at the plot on the bottom, you see the spin down rate evolution. So before the glitch is having a very nice linear evolution, which is expected. And then there is the glitch, in which you have a very large negative step. So the spin down rate increases, the pulsar slows down faster, and there's an exponential like recovery towards the pre-glitch values. But there's always this sort of gap. So the pulsar doesn't recover completely, or not in this time scale. So these are glitches. This is what we understand by glitches. I will mention now sort of briefly what can produce a glitch, or what we think it could be. So starquakes was the first thing that people thought. The idea is that if pulsars rotate very fast, so the pulsar initially should have some sort of an oblate shape, and as the pulsar spins down and time passes, it should sort of regain a spherical shape because it's spinning slower. But however, the energy that the crust is able to store and the properties that people have calculated of the crust are not able to reproduce the activity of pulsars, of glitches that we observe in pulsars. So this idea is some sort of it doesn't work too much. It might work to trigger glitches sometimes, but we still need a full glitch mechanism that is able to reproduce the activity of some pulsars that is not depending on starquakes. So what we like is, or the most popular model at the moment is some sort of superfluid crust interaction. Essentially, the idea is that the superfluid neutrons that are under the crust are weakly coupled to the rotation of the star, and they can store angular momentum. That's the most essential idea, and this angular momentum can be shared sometimes with the crust. How this happens? Well, it turns out that if you make a superfluid rotate, part of the angular momentum is stored in vortices. So in this very old sort of experiment, they were able to photograph some vortices that generate as the containment of this superfluid rotates. But in the neutron star, people expect something similar. So these lines, so this is on the right hand, you have a sketch of the neutron star, and these vertical lines are superfluid vortices that form when the star rotates. Now, the thing is that because the star is slowing down, these vortices need to move radially outward in order to account for the slowdown of the pulsar. And if you stop that migration of the vortices, which is what people call pinning, so that if for somehow you were able to stop the migration of some vortices, and then the more of these vortices you stop, then you're storing angular momentum. And if you release them all of a sudden and all at once, then you have a lot of angular momentum that is released. And so just because of conservation of angular momentum, you accelerate the crust at the same time that you slow down the superfluid. And that would be a glitch. So this is just very quickly what the models are like. You can imagine that the microphysics necessary to describe all this is complicated, and it's inside the neutron star where we barely know exactly many numbers and many quantities and how things work. So this is complicated physics, and the input from the observations is also limited. But it's an interesting subject, nonetheless. So I'm going to move back to observational properties of the glitches. Something I wanted to mention is that it's very important to keep in mind. Glitches are very rare events. So this is the glitch rate. So how many glitches per year were observed for these pulsars as a function of the characteristic age. The characteristic age is just a dynamical time for the rotation of the pulsar. It's essentially the period divided by the period derivative. So you can see that there's only something like 3, perhaps 4 pulsars that are above 1. So only 4 pulsars might have more than 1 glitch per year, and all the rest is below this line. And I think it's fair, it's safe to think of about 1 glitch every 10 years. If you think about any pulsar and glitches, you should not think about more glitches than that. So they are rare, and this has been a problem for the studies because we've had to wait a long time for to have enough glitches to do any sort of statistics. And we'll talk now about glitch sizes. So this is work that did Rafael Fuentes, a master's student that we had in Catholic University a few years back. And so he put together a big list of pulsars that had been observed for long times and had been searched for glitches. So this is some sort of like a unbiased database to study glitches. And in this database, there were 141 pulsars that glitched, and in total there were 384 glitches. So this is all the glitches. This is the same data in the 3 panels in this plot. It's just different binning. And you can see that this distribution at least has 2 main peaks, perhaps more, but I don't think the statistics are good to define more peaks. But there's at least 2 main peaks in which we can immediately see the large glitches and the small glitches, which is a very obvious definition. And let me also mention what this shade area in the left-hand side of the plot means. That means that below something like 10 to the minus 2 microhertz in the glitch size, we are not sure that we are detecting all those glitches. This is sort of a conservative limit, but it's important to keep in mind that the shape of this distribution towards the lower end, towards the smallest sizes, is very unclear. It might not be like this at all. We might be missing a lot of glitches. Something else that is interesting, that's important, is that the large glitches, when you put them in a PP dot diagram, which is this diagram on the right-hand side, each point here is a pulsar, and we have P dot on the vertical axis and the period of the rotation on the horizontal axis. And you can see that the pulsars with large glitches, which are painted in red, they tend to be pulsars with the highest spin down rates. And then the studies that Rafael Fuentes did, we sort of we found that at the end this has to do with the rate at which the large glitches happened, and so because they sort of they happen more often once the spin down rate is larger, for larger spin down rates. Something which is different, though, I mean, the distribution of the glitch sizes, we can see that it's at least bimodal. However, the distribution of glitch sizes for individual pulsars are very different, and this is something that it's interesting. So these are the 8 pulsars with 10 or more detected glitches, the only 8 pulsars with more than 10 detected glitches that we know, for the only ones for which we might expect to do some statistics. And then here we use some criteria to select which is the best distribution that can describe this size distributions. And I want you to just focus on the blue ones and the yellow ones, the ones that I marked the names of the pulsars with yellow and blue. So there are 2 Gaussian pulsars here, 0537, and then the Vila pulsar, which is on the bottom left. So those are Gaussian distributions, meaning that there's some sort of preferred size for the pulsar. However, the pulsars that I marked in yellow, these are power law distributions, and which is a complete different, it means something completely different in terms of the glitch mechanism, the glitch trigger, etc. And also in here in the yellow shaded area, we marked the area under which we think that maybe not all pulsars, not all glitches have been detected. Let me go back to looking at the full all this database, because we can calculate something that is called the glitch activity. The glitch activity is essentially when you add all the spin-ups due to glitches and divide by the time that in which they occurred. But when you do that for individual pulsars, is because the statistics are very low, it's not a very good number. The uncertainty is very, very high. So what we did is something that was done first in the year 2000 by Andrew Line, which is just the pulsars according to the spin down in boxes. And then we used all the pulsars in that box to calculate the glitch activity, and use even those pulsars that have not glitched. So in this plot on the top is the glitch activity that we calculate for these groups of pulsars in the fat black dots, and the individual pulsars are put there too, just to show how much they scatter. And the X shapes in the bottom of the plot with a horizontal, sort of with a single value, those are the pulsars that they have no glitch detected. So the main result here is that there is a very there's a very clear linear relationship between the glitch activity and the spin down rate. And so the bottom plot shows essentially that. It shows the glitch activity divided by the spin down rate. And you can see that there is a constant 1.2% value there. This value can be interpreted as something like the lower limit of the fraction of the moment of inertia of the superfluid that intervenes in the glitches. So this type of calculations, either for individual pulsars or for the full population, somehow tells you the size of the superfluid, or the relative size of the superfluid that is making the glitches. However, you can see this is again the same plot, the plot that shows the fraction of the spin down rate that is reversed by glitches, or the glitch activity divided by the spin down rate. And you can see that the regime, this 1.2%, fails for both extremes, for high spin down rate pulsars and for low spin down rate pulsars. So we proved in this paper that for the low spin down rate pulsars, what happens is that we have just not observed them long enough to have detected large glitches. So we saw before, large glitches tend to show pulsars with high spin down rates, but that's because we only started observing pulsars about 40 years ago, or maybe 50 years ago. And these large glitches, they need more time than that. So maybe in 100 years, we're going to be able to show this plot and it's going to be totally flat, or maybe not. Maybe there's still something else we don't understand. But we proved that we cannot rule out, at least at the moment with the statistics, that all the pulsars to the left of this orange line that I plotted here should follow the same trend, the 1%, 1.2% trend. However, the pulsars to the right-hand side of the orange vertical line, those pulsars, there's something intrinsically different. They don't seem to follow this trend. And that's something that is, well, it's not understood. The crab pulsar is one of the best examples of that. Now, something interesting is that these are again the 8 pulsars that I showed you before, the 8 pulsars for which we have more than 10 glitches detected. And again, look at the ones that are marked in yellow and blue, just to follow some examples. So the Vela pulsar, when you calculate its individual glitch activity, this is again the same plot that shows the fraction of the spin down reversed by glitches, or the glitch activity divided by the spin down rate. And you can see that these pulsars, even though they have completely different size distribution, some of them have a Gaussian distribution for the sizes, and others have a power law distribution for the glitch sizes, even though they all satisfy this 1.2 or something percent, meaning that perhaps if this 1.2% is related to the size of the superfluid that make glitches, means that they all have the same size, or they all tap from the same superfluid perhaps, but somehow something determines that they do it in a different way. Some of them having only large glitches, which is the case of the Vela pulsar or the other pulsar that has a Gaussian distribution of glitch sizes, or some of them prefer a power law in which their sizes are just any size. In this plot on the bottom left, I show the glitch sizes versus time for this yellow Vela pulsar and this, for this Vela pulsar in blue, and for the yellow other pulsar, which is a pulsar that has a power law scale for glitch sizes. And you can see that the behavior is different. However, they all seem to follow this 1.2% rule, which is something that somehow we will need to explain eventually. Okay, so I will talk now about small glitches. So you can see that to make these studies complete, all what I showed before, it is very important to understand well the lower end of the distribution. The higher end is easy. Detecting large glitches is very easy. In fact, it's very hard to miss them in the data. However, the small glitches are not easy to detect. And we don't know how many glitches are as we go small in size. So this is something which is very important, and it's also important for all the models. Well, this sorry, this is actually what I had just said. So these are just timing residuals for the crab pulsar, and sorry. Okay. Sorry, the Zoom window blocks my screen and I cannot see the plot. Okay, so these are timing residuals for the crab pulsar on the top. It's the same data, but in the top is only nu and nu dot fitted. So, well, you can see a very clear cubic term, double dot term, but that is important. And there's a glitch that you can already see there. If you do the nu double dot fit, so you fit for the second derivative of the frequency, you see more details of the behavior of the residuals. And you can see that the glitch is still there, but then there are other features that might appear sharp or cuspy, like glitches or not. And this is what I mean, that when glitches, or when you start looking for glitches in the noise, you might find many or you might not. It's a uncertain process. So we some years ago we wrote some detectability limits for the glitches, and essentially we established that they, well, something that people knew from before anyway, is that they depend on the cadence. So the more often you observe pulsar, the smaller the glitches you can detect. And also, obviously, you need a good sensitivity. If your error bars are too large, you might not be able to detect anything. So in these plots, seems a bit messy, but I will explain. So essentially, this is the jump in spin down rate on the vertical axis versus the jump in frequency for a glitch. So this is actually one of the yellow pulsars that I showed you in the other slides. So this one has a power law size distribution that you can see in the histogram on the bottom. And above in the plot, in the scatter plot, we can see the individual glitches. Now, the horizontal lines that are plotted on the plot are detectability limits according to cadence or sensitivity. So anything above those lines cannot be detected. So we can see that the glitches lie in the area in which we can detect, but we don't know how many glitches are to the left of these lines or above these lines, because we cannot events there. So we really don't know what happens with the glitch distribution of this size. Sorry, with the size distribution of this pulsar, because detectability options. And in this case, we need to really improve. We need at least to observe, for example, daily this pulsar and with a very high sensitive instruments in order to probe the distribution of sizes towards the lower end. The same happens to the other pulsar that we see there. This is another example. This is a Gaussian pulsar. This is O537. So this one has a Gaussian distribution of glitch sizes, which is plotted in the histogram on the bottom. And the glitches, so all sort of like gather in a very specific section of this plot. And the detectability lines are somewhat further away. And one might argue that perhaps we have already detected all glitches except in some of the small ones. So in this case, this would not be a problem. Who knows? The Villa pulsar looks something similar. So another reason to look for small glitches is the plot in the right hand side. It shows the size of a glitch versus the spin down rate. So these are this is from 2011. So there are more glitches now detected, but you can see that for very low spin down rate pulsars, we can detect actually very small glitches. So with sizes of the order of 0.01 or 10 to the minus 4. However, for high spin down rate pulsars, there are no events detected with those sizes. There are no events detected below 10 to the minus 3. And for example, the pulsar I'm showing in the left-hand side plot is I marked it on the right-hand side plot with the same sort of purple thing. And you can see that it lives there, and that we could have detected glitches smaller than that, but they are not there. And anyway, the question is, something that I would like to know. Is this part of is because the pulsars with higher spin down rate are noisier, so we cannot detect these glitches, or this is something intrinsic from the glitch mechanism? So these are the reasons to explore the small size glitches. I'm gonna take some time to move. The Zoom window blocks my screen, and I don't see my mouse, so this is complicated. Okay. Sorry about that. Okay.
Actually, I cannot see the pointer.
Can you see the point?
No. You can't see the pointer, actually.
Okay, yeah, no, I can't see it either. I don't see it. So anyway, that's why I'm describing everything with words. Okay. Okay, so now we'll talk about Vela and the what we've done with this pulsar. So Vela is a young pulsar. It's very famous. It's a very bright pulsar, and it's been it's been studied a lot because it's very bright, and it's very known. It's very famous for its large and frequent glitches, and with frequent. It's not that frequent, but it's one large glitch every about 3 years, and the large glitches are about the largest that we know of. So in the plot on the right-hand side, I'm just showing the evolution of the frequency between something like 1981 and 2007, I think. And this is the data that we analyzed. This data was taken by the Mount Pleasant Observatory in Australia for all these years, except in the gaps that you see there, in which they were changing instrumentation. And but the idea of these observations were to observe the pulsar essentially continuously. So they observed the pulsar every day during the whole day, except in the few hours in which Vela was under the horizon. So we want to use this data to study small rotational irregularities, not to study the large glitches, which is what people have always done. People normally, all the studies of the Vela pulsar using this database have been used by, I mean, the idea has always been to study the large glitches, the exponential recoveries, trying to detect the glitch rise of the frequency, which are all very interesting things. However, there has not been any study in which people look for the small glitch way, and there's no sort of like a complete catalog of the glitches. The only exception is perhaps the study by Cordes in 1988, and who studied the data just before this data set. So they studied data from 1968, which is from when they discovered the pulsar, up to 1983. And they did some sort of study in which they studied the small rotational variability, and they also they didn't discover many small glitches, which is part of our result. Anyway, so we did a search for glitch-like signatures. So I'm going to explain this plot. So if, as I said before, as a difference to timing noise, glitches are some sort of a sharp feature in the timing residuals. So a sharp feature, something like a discontinuity in the derivative of the phase. So that's what we're going to look for. So what we did in this search is to, for example, just take the first plot on the left-hand side on the top. So we do a fit for the points that are plotted in dark squares, and then we study the residuals of the data that is the open square data relative to that fit. And if that fit has some sort of a quadratic shape, that means that it follows the equation on the top, that means that there was a change in frequency and a change in the spin down rate. If the change is only linear, like in the bottom plot on the left-hand side, then that means that the change in the spin down rate was very small or undetectable. So there was only a frequency change. And this is the signature of a glitch. That's exactly the signature of a glitch. So we did a search, an automatic search that essentially moved TOA by TOA, adjusting 20 days of data and studying how the behavior of the next 10 days of data were relative to that first fit. You can find more details of this in our paper that is in the archive. And But we also search for signatures of with other signs of delta nu and delta nu dot. So in the left column in these plots, I show glitches, which is what we expect from a glitch, what we name, we have named glitches. So delta nu is positive, delta nu dot is negative. But we also search for what we called anti-glitches, which is a negative delta nu and a positive delta nu dot, exactly the opposite thing, which gives you exactly the inverse signature. But we also look for what I call something like timing noise-like sort of signatures, which is when the two changes have the same sign, including the possibility that the change in frequency is 0. So this gives you, especially when the change is 0, that gives you, that means that the derivative of the phase is continuous across the event. So it gives you more like a soft evolution of the phases. So that is more a bit like what timing noise is like. So we did a search for these three, all these type of signatures, and obtained many different events, and which we will analyze now. So the plot on the left-hand side is delta nu dot versus delta nu. So this is the size of the glitch. And in the diamond symbols show the non-large glitches that well-known, I mean, these have been known for years now, during this study period. So there are more glitches in this part of the diagram, but we are only plotting here those that
Crystal, may I ask?
correspond to the time interval that we analyzed. Yes.
So did you check your method on the simulated data without glitches? So you can...
Yes, we have. Yeah, I mean, if you don't have any glitches and you don't introduce noise in your data, you don't find anything.
Well, if you do not introduce noise, I understand, but you simulate data with noise and you test your method for false positive probability.
If you introduce noise in your data, for example, with a given like red noise, for example, with some spectral signature properties, you recover events too. And a good, yeah. You want to say something more?
What is probability? So you recover actually something like false positive, right? So in these false glitches, how frequent they are?
Okay. If you simulate data and with noise, with a red noise signature, with a given spectral properties that actually reproduce sort of very well what the Villa pulsar's residuals look like, and you then run this method to detect glitches, you find a lot of anti-glitches and small glitches, exactly as I'm showing here.
Mm-hmm. Okay.
So, yeah, okay. Like, I will comment a bit about that. So essentially, well, these are the results. We find a lot of glitch candidates that we called and anti-glitch candidates that live on the left-hand side of the plot, very far from the glitches, and almost in equal numbers. So the histogram on the right-hand side shows how many, these are the numbers, you know, of objects found, and the size, the glitch candidates and the anti-glitch candidates distribute sort of equally, and in similar numbers. And they're very detached from the other glitches, and there's no continuity, there is no excess of, there's no activity of glitches above 0.01 microhertz or so. And we know, because of the detectability things and like how the method works, that there's nothing else there. So the glitches live at around 10 microhertz, and there's a real deficit of glitches towards smaller events until you reach all these sort of events that we detect, which I believe, and we believe, these are not glitches or anti-glitches. This is just noise that we have been able to characterize with glitch-like signatures because the observations are not continuous. We have, I mean, I said that the observations are continuous, but you still have to separate them between in a discrete points. So we are not trying to say that these are events that actually happen. We are saying that we are characterizing the noise with a glitch model, and we can, and this is the result. But the important point here is that there's no small glitches. There are no glitches, there are not a lot of glitches of 0.1 size, for example. It's only one that we found, or a couple. So that's the main message here. I'm going to talk about these two. So these two events here are the only ones that actually breach the previously known glitches and the collection of noise-like events. And these ones we studied in detail, and they seem to be real glitches. Considering the definition that we have for glitches, it's very hard. There's no way to actually dismiss these ones as glitches. Here I show the phase residuals for the two of them. The smallest one is, besides the fact that it's very small, you can see that the signature in the phase residuals is very clear. And when you fit for the glitch, you get flat residuals. And for the bigger one, if you fit the phase residuals with a jump in frequency and frequency derivative, you still get a very large signal, which is an exponential decay. So we actually fit an exponential decay for this, for the largest of the two new small glitches. So yeah, these glitches had not been reported before because this data had never been searched for small glitches actually. But the main result here is that these are the only events that we found in this area of this part of the diagram, and there's nothing else. And we are sensitive to those events, but there's nothing else. These are the results of all the events. You know, I told you that we had looked for glitches, anti-glitches, but also for events that have the same sign in delta nu and delta nu dot, which is what I try to summarize in this diagram. So you can see that all the events that are found by this method live approximately in the same area of the diagram, considering the signs, and that the real or the non-glitches that we knew from before are detached from them. And this is similar to something that the Cordes had found. They also sort of had a method which is completely different to what we did to identify what they called microjumps. And they also, as you can see in the top and the bottom plot on the left, they also identified events at a similar size scale that we did, which are also completely separated from called macrojumps, which are the large glitches of the Villa pulsar. So this is consistent. The number of events in each of these quadrants in this plot is comparable. There are also a lot of events that have an undetected jump in one of the components, which we plotted with X and plus signs on the plot. And so our interpretation is that all these events are perhaps not real events in which the frequency suddenly changed. This is noise. This is the noise. This is a very characteristic thing of noise. Noise is an up and down sort of thing. And whether the right way to characterize the noise is with discrete jumps in frequency or frequency derivative is something that we still need to investigate more. These are examples of the macro irregularities that we found. So in the top, I'm showing the frequency. So this is the frequency of the pulsar without the main slope. So these are residuals, just to make it flat. But we can see that the frequency is also, moving up and down. This is in between glitches. There are no glitches in this time window. And in the very bottom, there is the spin down rate residuals too, because the spin down rate also has a slope. So I just removed that slope. And you can see that the spin down rate is not exactly smooth. It has events in which it increases significantly and then and also oscillates continuously. And when the spin down rate increases, you can see the effects in the frequency. In the middle panels, I showed what our method detected, and you can see that, for example, well, in these two middle panels, one of them shows the jump in frequency and the other one in frequency derivative, and they can be positive and negative. So this includes glitches, anti-glitches, and all sort of events with some combinations that you can make between these two steps. And you can see that even though some of the changes in the frequency or frequency derivative are actually detected, not all of them are, because not all of them well satisfied our criteria to actually be fitted as a glitch or an anti-glitch or any sort of event. And because perhaps this is not the ideal method to characterize timing noise. So yeah, I wanted to make that clear. We're not saying that the rotation of the pulsar is a collection of discrete jumps. It could be, but maybe not. It's something that needs a lot more study. The main idea, the main result is that the glitches in the Vela pulsar are all large, and they're actually not small glitches or not a big quantity of small glitches. They're all large glitches, and the distribution is likely to be very Gaussian. And the small glitches maybe belong to a different component of the distribution, but they happen at a very, very low rate. Okay, well, this is what I had just said. So yeah, the deficit of small glitches is real. It's not an effect of detection issues. We've proven that. If you compare the occurrence of large glitches above 10 microhertz and the other glitches, there are 4 times more large glitches than small glitches. So this is something which is interesting. So however you're going to explain the Vela pulsar glitches, this has to be included in the models. And besides the glitches, there's a constant activity, which is a very low level, that can at least partially be modeled by step changes in frequency or frequency derivative. And this is just to finish up. We had done a similar study on the crab pulsar, and we found something very, very similar. The crab pulsar, in general, the glitches of the crab pulsar are smaller than the Vela pulsar. They're more like, well, you can see here, the Vela pulsar has glitches that are of the order of 20 microhertz. They're not even in this scale on this plot. So in this plot, I'm showing the size of the glitches versus time. So we studied about 29 years of the crab pulsar, and we detected a lot of these candidates for glitch or anti-glitch, which at the end, this is the noise that is been just characterized with these numbers, and then the glitches that we knew previously. And so here we also found that there is some sort of separation between the glitches and this noise component, because there are no anti-glitches that beyond certain size. So again, we think that there's the noise component and then the glitches living on top of that. Or maybe everything is the same mechanism, but that mechanism has a break. There is a size above which there's only glitch-like signatures, not anti-glitch, not anything else. And below that, there is anything. Either way, this is a real feature. And so just to conclude, so some sort of summary. So a fraction of timing noise could be actually caused by rapid spin down changes. This has been studied by people, and which can be caused by different magnetospheric states because the pulse profiles seem to change in a correlated way. Some of these can be modeled with glitch-like signatures. We have just shown, even though we cannot, we don't have access to the profile data, the pulse profile. We can see that the noise also can be modeled with glitch-like signatures. That means that we also, perhaps you can also use delta nu steps at some point. And then not all pulsars glitch the same. We saw that they might have different size distributions. Regardless, the size of that, they all seem to reverse their spin down rate by about 1% via glitches. And finally, there's a real deficit of small glitches in the crab and Vela pulsars. And the question is whether that is a common behavior among young pulsars or not. And well, that's it. Thank you very much.
Thank you very much, Cristobal. Well, perhaps questions? Well, questions? Peter, does someone want to ask question?
Not yet.
What do you think about, well, perspectives of this activity? So you can put a lot of energy into this field. You can accumulate a lot of data, but well, it seems that well, theoretical interpretation is quite well not certain. Am I correct?
I don't hear very well. I think you asked about the theoretical interpretation. Yeah, it's hard to know, but as I mentioned maybe at the beginning, okay, there are two things here now. One of the things is that why there are no small glitches, and that is it's complex. The Vela pulsar perhaps it's easier to explain because all the glitches are large and they seem to have the same size. So you could explain that by just saying that you accumulate vortices and then they reach a threshold and then they all unpin and then you start accumulating them again. And then once you reach the same threshold, that you unpin them and generate another glitch of similar size again. And that explains why they are sort of regular every 3 or so years and why you have a similar size. And then it also explains why you wouldn't have too many small glitches. So the lack of small glitches in that model perhaps is understood. With the crab pulsar is a bit different because the crab pulsar behaves differently in many respects. Its activity is very low for if you consider the spin down rate it has. It has a very high spin down rate and you would expect it to glitch a lot more, but it doesn't. And so in this case, it's harder to explain why there would not be that many small glitches. On that, I don't know. And regardless, and talking about the timing noise part of the rotation, which is the other irregularity that we see in the rotation, I think it makes sense that we are seeing part of the magnetospheric activity. The magnetosphere is doing something, and we should be able to see that as accelerations or decelerations of the rotation. That's my point of view.
Okay, but then what would you expect of theorists? Do you expect them to construct a theory of magnetospheric activity which would predict something like this and then compare with observations? Or what, as far as I know, the theories of pulsar glitches associated with this light service, pinning and unpinning, is developing very slowly, I would say. I see no great progress in this field. So what do you need from theorists?
That's a good question. I don't know. I think, for example, normally what has happened in this glitch science is that while theoreticians are working on something, the observers are working on something different, and we cannot talk. But because in general, the theories have been, for example, trying to model how the glitch happens, the details of the glitch, like how the frequency increases in the crust, etc. And that in general cannot be observed. Although we have to remember a couple of years ago, there was actually an observation of a Vela pulsar glitch in which they had sort of resolved the glitch. And there was a lot of physics that we learned from that. I think that if we should continue studying things like this, I believe that by studying the lower end of the size distribution can actually teach us a lot. And I would expect that people who do models of glitches, if they model what triggers the glitch, and if they could start to try to reproduce the glitch size distributions that we are now uncovering, that would be interesting. And I think that's something that could be done.
Wow. Okay. So what about more questions, comments?
May I ask? May I ask?
Sure.
What glitches in magnetars? How many glitches from magnetars are known now?
I have, yeah, there's a plot that shows, and I didn't mention it here. So magnetars are known, or people used to say magnetars a lot because the rotation of magnetars is very, very noisy. In this size distribution, we're showing the magnetars with its dark histogram. So if you see this, first of all, the glitches of the magnetars are not part of the large glitch component. They are just there. There are not too many, but that could be an effect that the fact that there are not too many magnetars. And also, there are not too many studies in which magnetars are observed continuously, or not continuously, but regularly, and monitored and searched for glitches. That is, the study of magnetars is mostly focused on study the pulsar around the times of the bursts, unfortunately, because we cannot do follow-ups for very long times with the X-ray satellites, essentially. So it's a bit of a bias in that sense, but they are noisy, and some of the magnetic glitches have a burst associated with them, so they are sort of radiatively loud, which is different from radio pulsars. I don't know whether that answers your question.
Okay, but there are high B pulsars, which the transition stage to magnetar. Do they glitch?
Yes, yes, they do. There are a couple of pulsars that are actually in this sort of transition stage that you mentioned, in the sense that they are otherwise sort of like standard radio pulsars, but they have shown magnetar-like activity. They have glitches. The glitches are somewhat strange or different, if you want, but it's very hard to tell why they would be different, or whether the high magnetic field has anything to do with that. It's hard to tell.
Okay. So what about more questions? If no, then we must thank speaker again. Thank you very much, Cristobal. It's a nice talk. So the next seminar will be the next week. That will be Beatrice Winton. We will be speaking about magnetars. So this seminar is over. Thanks all of them who attended the seminar. And goodbye.